This is Bio 181, Chapter 6 video. We're going to be comparing endergonic and exergonic reactions. So endergonic reactions are going to require energy, right? Whereas exergonic reactions are going to release energy. So endergonic reaction. These are going to be reactions that are basically going to create things that are in general more ordered. So it's going to oppose the first law of thermodynamics. So in this type of reaction, if we had a graph, okay, we're going to start with low energy and we're going to end with high energy. So if we were to graph over time here, okay, the reactants are low, and then you're going to end up with high products. There's a little hump here. Sometimes it takes extra energy. It's called activation energy to get the reaction going. Okay. But so over here, this is our reactants. Reactant. Right. And then over here is the product, what you end up with. So it requires energy to climb up here. All of the energy that's required is going to go basically into the chemical or potential energy in the products, right? And often this energy that's added is going to be in the form of the molecule called ATP. It's going to help provide this energy, right? Now the opposite is true for exergonic reaction. So exergonic reaction, same idea, right? Over here, you've got energy on this vertical axis, okay? So, but in this case, you're going to start with high energy molecules. You're going to end with lower energy molecules. And again, this is going to occur over time. So we're going to move from left to right. So at time equals 0, okay, we're going to start with reactants that have relatively high energy. It's going to take a little bit of energy for that reaction to get started. And then the products are going to have low energy. So again, the product over here, lower energy, and the reactants higher energy. Where is that energy going? Well, that energy can be used to make ATP, so that's possible, which is the energy molecule of the cell. Okay. It can also be used to do work. To do work. So work could be anything like move an animal or move ions or build up a molecule. So whatever that looks like. All right. So free energy, this is just the term for the energy that's available to do work in a reaction. There's some fundamental energy in an atom, the nuclear force, the strong force, you're not able to get that out, but some of it you can from the electrons. Gibbs free energy is the energy at a constant temperature. So we're just going to assume that for this class, that we're always talking about a constant temperature. So we're not changing that variable. Delta G, this delta, this is a capital D in Greek, delta, and it just means change. So it's the change in the energy, and it's going to refer to the change in the energy from the reactants to the products. All right, so this is the reaction. I basically diagrammed this before. The only thing I want to point out here, endergonic reactions. We talked about the laws of thermodynamics. Things generally go from so things generally go from high order to less order. And so in an endergonic reaction, it's actually going to require energy. That means we're going to go opposite to the natural state of affairs. So generally the products are going to be more ordered. or they might be larger, say, or have more bonds compared to the reactants, right? Which may be less ordered, less order. Okay, and they may be more, smaller, smaller molecules, okay? So just in general, whereas the exergonic reaction, right, we might start with a large molecule here. It's got a lot of energy, say, in the bonds. So say we have a polymer, which is a big, long molecule, and we end up breaking it apart into a whole bunch of individual pieces. As we do that, the energy is released. This is going to be a spontaneous reaction. Things more naturally like to break apart and have more disorder. Okay. Words for that. So anabolic, that's going to be when you're starting with, a few molecules that are smaller, you put those together and you get larger chains of molecules. You're building up something bigger. So that's anabolic. You're going from small, right, to large. Okay, and this is going to require energy. So we're going to use ATP, which is our energy molecule. Whereas for a catabolic reaction, that's just the opposite. So a catabolic reaction is the opposite. If we're to go this direction, so from the right to the left, we're going to release, energy. I'll just say we're going to release energy. Sometimes it does take ATP to start that process, right? But in general, we're going to go from large molecules, large to small in a catabolic reaction. Okay. All right. Metabolism, this is just a vocabulary word that refers to all of the chemical reactions that sustain life. So it's a very broad term, all chemical reactions, okay, that sustain life, that are required to support life. Sustain or are required for life. Whoops. Life. So this could be getting energy out of the food that you eat for your digestion. If you have a high metabolic rate, that means your reactions are happening pretty fast. If you have a low metabolic rate, then they're happening slower. All right, that's it for this video.